Tonight, we're going to look at something that surrounds you right now, at this exact moment, in every direction you can point. Empty space. Or at least, what you think is empty space. Because here's what physicists discovered over the last century, and what most people still don't fully understand. The vacuum is not empty. Not even close. The space between your fingers, the space between the molecules of air in this room, the space between galaxies stretching across billions of light years, all of it is filled with something. Fields, energy, particles that flicker in and out of existence so fast we can barely detect them, and forces that press on every surface in the known universe. And by the end of tonight, you're going to understand why the emptiest places in the universe are, in a very real sense, never empty at all. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what seems obvious. Empty space is empty. You remove all the air from a container, you pump out every atom and molecule, and you're left with nothing. A vacuum. That's the classical picture. The one physics operated with for most of its history, and the one that feels completely intuitive. The container has no gas, no matter, no particles. Nothing is in there. It should sit perfectly still, contribute nothing, do nothing. For a long time, that was exactly what physicists assumed. It wasn't laziness or lack of imagination. It was just the simplest working model, and for most purposes, it was accurate enough. Classical mechanics, the framework that explained the motion of planets and cannonballs and pendulums, treated the vacuum as a passive stage. Nothing there, nothing happening. The motion of objects depended on forces between matter, between things that existed, between things you could point to. The vacuum was just the absence of those things, and for centuries, that assumption worked well enough. It explained the behavior of gases, the motion of planets, the spread of heat. The vacuum was just an absence, a background against which everything else happened. Newton's laws didn't need the vacuum to do anything. Maxwell's equations for electromagnetism described waves propagating through space, but even those were thought for a time to require a medium, a substance for the waves to travel through, something filling the vacuum that could carry the oscillation the way air carries sound. They called this medium the ether. The idea was that light waves, like all waves, needed something to wave in. Space couldn't be truly empty if light was traveling through it. There had to be something there. The ether was a serious scientific concept, not a fringe idea. It was taught in universities. It was assumed by the leading physicists of the 19th century, when the famous Michelson-Morley experiment in 1887 failed to detect any motion of the Earth relative to this supposed ether. The conclusion was not that space was something. The conclusion, eventually, was just that the ether didn't exist. The vacuum was still nothing. Just nothing without an ether inside it. Light could apparently propagate through a genuine vacuum. Strange, uncomfortable, but experimentally undeniable. For a while, the vacuum was once again just the absence of everything, until the next generation of physics arrived, and with it, an answer to the question of what empty space really is, an answer that nobody in the 19th century would have believed. According to quantum field theory, the framework that describes how particles and forces behave at the smallest scales, fields are the fundamental reality of the universe. Not particles, not matter in the traditional sense. Fields. A field is something that has a value at every single point in space. Not in some points. Not in the points near matter or energy. Every point. The electromagnetic field, for example, permeates all of space. Every point in the universe sits inside the electromagnetic field. When it oscillates, those oscillations are what we call photons, the particles of light. The electron field permeates all of space. When it's excited in the right way, the excitations are what we call electrons. The quark field permeates all of space. The Higgs field permeates all of space. Every particle you know of, every force you know of, is an excitation of an underlying field that stretches across the entire universe. The field is always there. The particle is what you get when the field vibrates in a particular way. Remove all the particles. Remove all the radiation. Remove all the obvious energy sources. The fields are still there. They pervade the space anyway, because they don't need matter to exist. They are more fundamental than matter. Matter is made of them. This is a fundamentally different picture from the classical one. In classical physics, matter sits in space. Space is the background. In quantum field theory, fields fill space. They are the background. And the question then becomes, what are those fields doing when nothing is obviously exciting them? When there are no atoms around, no radiation, no energy source? What are the fields doing in that supposed void? The answer quantum mechanics gives is that they are still doing something. They cannot stop. They are forbidden from stopping by something built into the mathematics of reality at the deepest level we know about. This is where things get strange, and it comes from a principle at the heart of quantum mechanics. The Heisenberg uncertainty principle. You've probably heard of it in the context of particles. You can't know a particle's position and momentum simultaneously with perfect precision. The more precisely you know where it is, the less precisely you know how fast and in what direction it's moving. That's the most commonly cited version. But the uncertainty principle applies more broadly. It applies to pairs of quantities that are mathematically conjugate, linked in a specific way by the structure of quantum mechanics. Position and momentum are one pair, but also energy and time. The more precisely you pin down the energy of a system over some time interval, the less precisely you can know when that energy exists, or equivalently, how long the system stays in a particular energy state. And, critically, for our purposes, it applies to quantum fields. Each mode of a quantum field, each possible frequency of oscillation, behaves mathematically like a harmonic oscillator, like a pendulum, like a mass on a spring. And for each of those oscillators, there is a version of the uncertainty principle that says, you cannot know both the value of the field and the rate of change of the field with perfect precision at the same time. If the field is exactly zero at some moment, you can't know how fast it's changing. If its rate of change is exactly zero, you can't know what value it has. The product of the two uncertainties must always exceed a certain minimum, proportional to Planck's constant. This is not a limitation of your instruments. It isn't a measurement problem. It's built into the nature of reality at the deepest level we've found. The consequence is that even in a vacuum, even in a region of space with no matter, no radiation, and no energy put into it deliberately, the fields are constantly fluctuating. They can't settle to zero. They can't be perfectly still. They must always be doing something, jittering, oscillating at the quantum level. This is what physicists call zero-point energy. The energy the vacuum possesses simply by existing. The minimum energy any quantum system can have. And it's not zero. It can never be. A pendulum at rest would have zero energy. But a quantum pendulum can't be exactly at rest, because that would require knowing exactly where the bob is and that it's not moving simultaneously. The quantum pendulum oscillates even at its lowest energy state. It has zero-point energy. Every oscillator in nature does. Every mode of every quantum field does. And there are fields everywhere, which means there is zero-point energy everywhere. In every cubic meter of space, no matter how isolated, no matter how far from any star or galaxy or atom, the vacuum seethes. Think about what that means. Every point in space, everywhere in the universe, has a baseline level of energy that cannot be removed. You cannot take it away. You cannot cool a region below this baseline. You cannot, by any means available in physics as we understand it, reach a true zero-energy vacuum. The vacuum has an irreducible energy content, an energy floor. And that energy has real physical consequences, not theoretical ones, not ones that only show up in equations and can be dismissed as mathematical artifacts. Real, measurable, confirmable consequences. The first place scientists started to take this seriously was in the early development of quantum electrodynamics, the theory of how light and matter interact. Developed in the 1940s by Richard Feynman, Julian Schwinger, and Sein Ichiro Tomonaga. Their theory described the interactions between electrons and photons with extraordinary precision. It predicted the behavior of atoms and molecules, the way light is absorbed and emitted, the magnetic properties of particles, all of it to many decimal places. With greater accuracy than almost any other theory in science. But it also predicted something that seemed like a problem. The vacuum, even empty space, should contain virtual photons. Photons that exist for fleeting moments as a consequence of quantum uncertainty, and then vanish. Virtual particles. This sounded absurd. Particles that aren't really there, appearing and disappearing in empty space. Particles that you could never directly observe because by definition they exist only in that brief borrowed interval before uncertainty demands they give back their energy. Most physicists assumed this was a mathematical artifact, something in the formalism that didn't correspond to any real physical effect. A useful calculational trick, perhaps, but not reality. Then the experiments happened, and they found that the virtual particles were not mathematical artifacts. They were real, in every sense that matters. They were doing things. In 1947, Willis Lamb and Robert Rutherford at Columbia University were measuring the energy levels of the hydrogen atom. Hydrogen is the simplest atom that exists. One proton, one electron. It had been understood since the 1920s, described by the Schrödinger equation with remarkable precision, and then refined further by Paul Dirac's relativistic equation, which also accounted for the electron's spin. The energy levels of the hydrogen electron, the specific rungs of the energy ladder the electron can occupy, were thought to be completely mapped out. Two of those levels, called the 2s1/2 level and the 2p1/2 level, were predicted by Dirac's equation to be exactly equal in energy, to have the same mass, to be perfectly degenerate. Lamb and Rutherford measured them, and they were not. They were shifted apart by a tiny but measurable amount. One specific level sat slightly higher in energy than the theory said it should be, relative to the other. This shift was about 1060 MHz, expressed in frequency units. Tiny, but unmistakable. Precise. Reproducible. And it had no explanation in any version of quantum mechanics that existed before quantum electrodynamics. But quantum electrodynamics predicted it. The virtual photons of the vacuum were interacting with the electron in the hydrogen atom. These photons, that technically don't exist in the conventional sense, were nudging the electron, tugging at it slightly as they flickered in and out of existence around it, perturbing its position slightly. And because the 2s and 2p levels interact with the vacuum fluctuations differently due to the different spatial structure of their wave functions, the fluctuations shift one level more than the other. The electron was being jostled by the quantum vacuum. The effect was small, but it was precisely predictable by the new theory, and the prediction matched the measurement. The vacuum was affecting the atom. Not hypothetically, not as a theoretical curiosity, measurably, quantitatively, with precision. This is called the Lamb shift, named for Willis Lamb. He received the Nobel Prize in Physics in 1955. And the Lamb shift remains one of the best-tested predictions in all of physics. Modern measurements of the Lamb shift in hydrogen and in heavier atoms have been matched by quantum electrodynamics calculations to more than 10 significant figures. The agreement between theory and experiment is among the most precise in all of science. And the cause of that shift is the quantum vacuum, the virtual particles flickering in the supposedly empty space around the hydrogen atom. The vacuum, the supposed nothing, was doing something. The Lamb shift is not just a historical curiosity. It remains one of the most actively studied quantities in precision physics today. Modern measurements of atomic energy levels have reached extraordinary precision. The hydrogen atom, in particular, has been measured using laser spectroscopy techniques to more than 15 significant figures. These measurements are used to test quantum electrodynamics with exquisite sensitivity. They also allow precise determinations of fundamental constants. The Rydberg constant, which governs the energy levels of hydrogen, is known to 12 significant figures from modern spectroscopy. The proton charge radius, the physical size of the proton, can be inferred from measurements of the hydrogen Lamb shift. In 2010, an experiment using muonic hydrogen, a hydrogen atom where the electron is replaced by a muon, a heavier cousin of the electron, measured the proton's size with unprecedented precision. Muons orbit much closer to the proton than electrons do. They interact with the proton's charge radius more strongly. The Lamb shift in muonic hydrogen is more sensitive to the proton's size. The result was surprising. The proton charge radius from muonic hydrogen disagreed with the value from regular hydrogen measurements. The difference was small, about 4%, but it was statistically significant. This became known as the proton radius puzzle. Something was wrong. Either the measurements were subtly incorrect, or quantum electrodynamics was missing something. For several years, the discrepancy persisted. Eventually, improved measurements of regular hydrogen, using more precise laser spectroscopy techniques, narrowed the gap. Current measurements are consistent with each other, suggesting the earlier discrepancy was a systematic error in the regular hydrogen measurements rather than new physics. But the episode illustrates the power of precision Lamb shift measurements. They are sensitive enough to detect the physical size of the proton. They are a probe of matter at the scale of 10 to the negative 15 meters. And they work by measuring how the quantum vacuum interacts with different atoms. The vacuum fluctuations around muonic hydrogen are different from those around regular hydrogen because the muon is different from the electron. The vacuum's interaction with the atom is specific. It's not uniform. It depends on the precise quantum state of the particle inside it. And measuring those differences reveals the structure of matter at scales far below anything that can be directly imaged. The quantum vacuum is not just a curiosity at the frontier of physics. It is an active probe of the structure of matter. A year after the Lamb shift was measured, Hendrik Casimir was working at the Philips Research Laboratories in the Netherlands. He was thinking about quantum electrodynamics and the virtual photons of the vacuum. And he had a conversation with another physicist, Dirk Polder, that led to a prediction Casimir initially found remarkable even by his own standards. Take two flat, uncharged metal plates. Place them very close together in a vacuum. No charge, no magnetic field, no obvious reason for them to interact. Casimir predicted they would attract each other. Not because of gravity, which, at the scales and masses involved, would be negligibly small. Not because of static electricity, since the plates are neutral. They would attract because of the vacuum itself, because of the quantum fluctuations in the space between them. The argument goes like this. The vacuum is filled with virtual photons. Quantum fluctuations of the electromagnetic field, flickering in and out of existence at every frequency, in every direction, at every point in space. All possible modes of the electromagnetic field, existing briefly in the vacuum, form a kind of pressure that presses on any surface. When you place two metal plates close together, you impose a constraint on those fluctuations. The plates are conductors. Electromagnetic waves must satisfy certain boundary conditions at the surface of a conductor. Specifically, the component of the electric field parallel to the surface must be zero at the surface itself. This means that in the space between the plates, only those modes of the electromagnetic field whose wavelength fits a whole number of times into the gap can exist. The wavelength must be a half-integer multiple of the gap distance. Half the gap, the full gap, 1.5 times the gap, and so on. Wavelengths longer than the gap simply cannot fit. They are excluded, suppressed between the plates. But outside the plates, there is no such restriction. All wavelengths, all frequencies, all modes of the vacuum fluctuation exist freely on the outside surfaces of the plates. This creates an imbalance. More vacuum fluctuation modes pressing on the outer surfaces of the plates than on the inner surfaces facing each other. The pressure from virtual photons outside exceeds the pressure from virtual photons between the plates. The result is a net force pushing the plates toward each other. A force with no source except the quantum vacuum. A force that comes from the imbalance between the unrestricted nothingness outside and the constrained nothingness between. Casimir published this prediction in 1948. The effect was small, incredibly small. But it was measurable, at least in principle. The force scales as 1/4 power of the plate separation, halve the distance, and the force increases by 16 times. At a separation of 1 micrometer, 1 millionth of a meter, for plates, 1 square meter in area. The predicted force is about 1 millinewton. About the weight of an apple. Not nothing. At 10 nanometers, 100 times closer, the force becomes substantial. At separations of hundreds of nanometers, it becomes measurable with sensitive equipment. It took about 50 years for experimental technology to catch up with Casimir's prediction. In 1997, Steve Lamoureux at the University of Washington measured the Casimir force for the first time with sufficient precision to confirm the prediction. He used a torsional pendulum, a very sensitive instrument for measuring tiny forces, and metal surfaces separated by distances ranging from about 600 nanometers to 6 micrometers. At those separations, the Casimir force is real, detectable, and consistent with the theoretical prediction. The measurement matched the prediction to about 5%, limited by the experimental uncertainties at the time. Since then, the effect has been measured many times with increasing accuracy. Modern experiments can measure the Casimir force to within a few percent across a range of geometries and materials. The Casimir effect is not controversial. It is not speculative. It is confirmed physics. Measured in laboratories on multiple continents. Reproduced with multiple techniques. The vacuum is exerting a real, measurable force. Nothingness is doing something. And by something, we mean something specific enough to calculate, predict, and verify to several significant figures. What makes the Casimir effect important, beyond its immediate measurement, is that it shows the structure of the vacuum can be manipulated. By changing the geometry of your plates, by changing the material, by changing the gap, you change which vacuum modes are allowed and which are excluded. You change the force. This means the vacuum is not a fixed, uniform background that is the same everywhere. It has structure. It responds to boundaries. It responds to geometry. It can be shaped, at least in small and subtle ways. Different plate materials produce slightly different forces because the way a material excludes electromagnetic modes depends on its conductivity and dielectric properties. A perfect conductor excludes all modes that don't satisfy the boundary condition. A real metal with finite conductivity lets some modes through that a perfect conductor would exclude, which reduces the Casimir force slightly. These corrections are understood theoretically and observed experimentally. There are also interesting geometries beyond flat parallel plates. A sphere above a flat plate, 2 spheres, cylinders, corrugated surfaces. All of these have been studied, theoretically and experimentally, and they all show Casimir-like forces arising from the way the geometry constrains the vacuum modes. The vacuum responds to geometry. Nanotechnology has advanced to the point where the Casimir force is no longer just a curiosity. At the scales where nanoscale machines operate, separations of tens to hundreds of nanometers, the Casimir force becomes significant. It can cause nanomechanical parts to stick together, a problem called stiction, which is a portmanteau of static friction and adhesion. Tiny cantilevers in microelectromechanical systems can be pulled towards substrate surfaces by the Casimir force alone. Engineers designing tiny machines at those scales have to account for it in their models. The quantum vacuum is literally a factor in engineering decisions. Something that would have seemed absurd to any physicist before 1947. Something that most physics textbooks before the 1980s barely mentioned. Now it's in engineering handbooks. The void has become a design consideration. There is something even stranger about the Casimir effect. Under certain conditions, it can be repulsive. The standard Casimir effect between two identical metal plates in vacuum is attractive. But the specific sign of the force depends on the materials involved and what fills the space between them. In 1968, physicist Tim Boyer calculated the Casimir force for a hollow conducting sphere. He found that for a perfectly conducting sphere, the Casimir stress is repulsive. The vacuum fluctuations inside the sphere push the sphere outward, not pull it inward. The geometry changes the sign of the force. More dramatically, in 2009, a team at Harvard, led by Federico Capasso, demonstrated a repulsive Casimir force in the laboratory. They suspended a gold-coated sphere above a silica plate with a specific liquid between them, bromobenzene. The dielectric properties of the silica plate, the gold sphere, and the liquid medium, combined with the way they each respond to the vacuum modes at different frequencies, produced a Casimir force that was repulsive. The sphere and the plate pushed apart. The quantum vacuum was pushing things away from each other, not pulling them together. This is not exotic physics. It follows directly from the theory Casimir, established in 1948. But it shows the range of what the vacuum can do when you change its boundary conditions. It also has practical implications. Repulsive Casimir forces could, in principle, be used to reduce friction in nanomechanical devices. If you can engineer the geometry and materials so that the Casimir force is repulsive, nanoscale parts that would normally stick together stay separated. Frictionless bearings at the nanoscale, driven by the quantum vacuum. The engineering challenges are significant, but the physics is real. The vacuum pushes, pulls, and under the right conditions can be engineered to do one or the other. Now, the virtual particles themselves deserve closer attention, because this is where the vacuum gets genuinely strange and where the language can mislead. When physicists say virtual particles pop in and out of existence, that phrasing can create a misleading picture. Virtual particles are not the same as real particles. They do not have to satisfy the normal relationship between energy and momentum that real particles satisfy. A real photon always has energy equal to Planck's constant times its frequency. It travels at the speed of light. It has a definite momentum. A virtual photon is an internal line in a Feynman diagram, a calculational tool in quantum electrodynamics. It can have any energy and momentum, including combinations impossible for a real photon. So, in what sense are they real? The answer physicists give is that virtual particles are real in the sense that they produce real effects. The Lamb shift is real. The Casimir force is real. Virtual particles mediate the electromagnetic force between charged particles. In quantum electrodynamics, when two electrons repel each other, what's actually happening at the quantum level is they're exchanging virtual photons. One electron emits a virtual photon. The other absorbs it. The exchange transfers momentum. Momentum transfer is what force is. The repulsion you'd feel if you pushed two negatively charged objects together is the result of virtual particles bouncing between real ones. This is not a metaphor. It is the actual mathematical description used to calculate electromagnetic forces. The precise calculation of how electrons repel using virtual photon exchange in perturbation theory, agrees with experiment to about 10 decimal places. It is the most precisely tested quantitative theory in science, and it requires virtual particles. Without them, the calculation doesn't work. Without them, electromagnetism doesn't make sense at the quantum level. Every force in nature, at the quantum level, works through this same mechanism. The strong nuclear force that holds protons and neutrons together inside atomic nuclei is mediated by virtual particles called gluons. Quarks inside a proton are constantly exchanging gluons. The gluons carry the color charge of the strong force. Without that constant virtual particle exchange, without that activity in what might look like the empty space inside a nucleus, protons would disintegrate instantly. Atoms could not exist. Chemistry could not happen. You could not exist. The weak nuclear force, responsible for certain types of radioactive decay and for the nuclear fusion processes that power stars, is mediated by virtual particles called W and Z bosons. These particles are very heavy in their real form. About 86 to nearly 100 times the mass of a proton. They are difficult to produce and were only first directly observed at CERN in the early 1980s. But their virtual versions, the ones that mediate the weak force, are present constantly in every atomic nucleus in the universe, enabling the nuclear reactions that convert hydrogen to helium in the cores of stars. Without those virtual particles buzzing through nuclear matter, the sun wouldn't burn. No star would. Even gravity, in the frameworks that attempt to unify it with quantum mechanics, is thought to be mediated by a hypothetical virtual particle called the graviton. We haven't confirmed the graviton. Gravity is the one fundamental force that hasn't yet been successfully brought into the quantum field theory framework in a fully consistent way. This is one of the deepest unsolved problems in all of physics. But the logic points toward it. Force as exchange. Exchange as virtual particles. Virtual particles as vacuum activity. The vacuum is not empty. It is the medium through which all forces propagate. Remove the vacuum, and the concept of force ceases to have meaning. There is one measurement of the quantum vacuum's effects that stands alone in its precision: the anomalous magnetic moment of the electron. Every electron behaves like a tiny magnet. It has a magnetic moment, a strength and direction to its magnetism. Dirac's equation for the electron predicted that this magnetic moment should be exactly 2 in a certain natural unit, called the Bohr magneton. Precisely 2. A clean, exact prediction. But quantum electrodynamics, the theory that includes the quantum vacuum, predicts something slightly different. The virtual particles in the vacuum interact with the electron. Virtual photons are emitted and reabsorbed. Virtual electron-positron pairs appear and vanish around the electron. These virtual interactions give the electron a slightly different magnetic moment than Dirac predicted. Slightly more than 2. The deviation from 2 is called the anomalous magnetic moment. It's written as G-2 divided by 2, where G is the actual magnetic moment in the natural unit. The theoretical prediction of this quantity from quantum electrodynamics involves calculating the contributions of all possible virtual processes, all possible ways for the electron to interact with virtual photons and virtual particle pairs. These calculations have been carried out to extraordinary depth. The current, best theoretical value involves summing contributions from Feynman diagrams with up to 10 virtual photons. There are about 12,000 distinct diagrams at that order. Computing their contributions requires years of work and significant computer time. The result is a number known to about 11 significant figures. The current best experimental measurement was performed at Northwestern University and reported in 2023. It used a single electron trapped in a magnetic bottle and measured its quantum states with exquisite precision. The measured value and the theoretical value agree to about 1 part in a trillion, 1 in a million. This is the most precisely tested prediction in all of science. And what it's testing is the quantum vacuum, the virtual particles flickering around the electron. The zero-point fluctuations of the electromagnetic field interacting with the electron's charge. If the quantum vacuum didn't exist, or if it behaved differently than quantum field theory predicts, the electron's magnetic moment would be different. The agreement between theory and experiment, to 1 part in a trillion, is the most precise confirmation that the quantum vacuum is real and behaves exactly as the theory says. There is no measurement more precise than this in physics, and it measures, at its core, the effect of empty space on a single electron. There's a deeper layer to this, and it connects to something that most people have never thought about. The fields that fill the vacuum are not all equal. They have different properties, different ranges, different strengths. And one of them, predicted theoretically in the 1960s and confirmed experimentally by CERN's Large Hadron Collider in 2012, is responsible for something fundamental: mass itself. Not just the mass of some things, the mass of every massive particle in the universe. In the early 1960s, physicists were trying to understand a puzzle in quantum field theory. The theory of the weak force required its mediating particles, what would later be identified as the W and Z bosons, to be massive. Very massive. But the mathematics of quantum field theory seemed to prohibit massive force-carrying particles. The symmetry principles underlying the theory insisted the mediating particles should be massless, like photons. Several physicists, including Peter Higgs, Francois Englert, and Robert Brute, proposed a solution. What if there were a field that pervades all of space with a non-zero value? A field that's not zero, even in the vacuum. And what if other particles, by interacting with this background field, acquired mass? The particles would be slowed by the interaction, given inertia, made massive. It's a bit like moving through a medium. A particle with no mass moves at the speed of light. But if it interacts with a background field, it's continually being absorbed and re-emitted, slowed, given effective mass. This became known as the Higgs mechanism. The Higgs field permeates all of space. Every point in the observable universe sits inside the Higgs field right now. It's active in this room, in the space between the atoms in your body. What makes the Higgs field unusual is that it has a non-zero value in its lowest energy state, its ground state. When all other fields are at their lowest possible energy, they are zero, quiet. The Higgs field is not. It has a value everywhere, always, even in the deepest, most isolated vacuum. This non-zero background value is called the Higgs field's vacuum expectation value. It's about 246 giga-electron-volt in particle physics units, a permanent, universal feature of the vacuum. And it's not passive. Particles moving through space interact with this background Higgs field. That interaction is what gives them mass. The more strongly a particle couples to the Higgs field, the heavier it is. Electrons interact with the Higgs field, but weakly, so electrons are light. Top quarks interact with the Higgs field much more strongly, so top quarks are among the heaviest elementary particles known, about 184 times the mass of a proton. Photons don't interact with the Higgs field at all. That's why photons are massless and always travel at the speed of light. W and Z bosons interact very strongly with the Higgs field. That's why they are heavy, making the weak force a short-range force rather than long-range. The empty space you're sitting in is filled with the Higgs field at its vacuum expectation value. And that field, that background presence in the vacuum, is what gives all the matter around you its mass. Your body has mass because the particles that make it up are interacting with the vacuum, with what fills supposedly empty space. The connection between you and the vacuum is not poetic. It is literal. Your inertia, your weight, your resistance to being pushed around, all of it comes from your particles' constant interaction with the Higgs field, permeating the vacuum around and through you. The Higgs boson, discovered at CERN in 2012 by the ATLAS and CMS experiments, is the excitation of this field. It's what you get when you dump enough energy into the Higgs field to create a ripple in it. A wave. An observable particle. Peter Higgs and François Englert shared the Nobel Prize in Physics in 2013 for predicting it. But the Higgs boson is not the important part. The important part is the vacuum expectation value, the non-zero background that's always there. If you could somehow turn off the Higgs field, collapse its vacuum expectation value to zero, every electron, every quark, every massive particle would instantly become massless. Atoms would cease to bind. Chemistry would stop. The ordinary matter making up the world would dissolve into a chaos of massless particles flying apart at the speed of light. The universe, as we know it, would cease to exist. The vacuum is not decorative. It is structural. The fabric of the universe, the possibility of matter, the existence of chemistry and biology, and everything built from them, depends on what fills empty space. The Higgs field also teaches us something deeper about the vacuum, about a phenomenon called spontaneous symmetry breaking. Consider a pencil balanced perfectly upright on its tip. In that position, the pencil has a perfect rotational symmetry around the vertical axis. The system looks the same, no matter which horizontal direction you face. But that upright position is unstable. Eventually, the pencil falls. When it falls in some particular direction. It breaks the rotational symmetry. The underlying physics is still symmetric. Gravity pulls equally in all horizontal directions. But the ground state, the lowest energy configuration, the resting position, is the pencil lying on the floor, pointing in one specific direction. The symmetry has been spontaneously broken. The equilibrium has lower symmetry than the laws governing it. The Higgs field does something analogous at the scale of the entire universe. In the very early universe, when temperatures were extraordinarily high, the Higgs field was in a different phase. Its expectation value was zero. The laws of physics at those energies looked symmetric between forces that now look different. The electromagnetic force and the weak force were unified into a single electroweak force. Particles that now have mass were massless. The distinction between them was washed out by the intense thermal energy. But as the universe cooled, the Higgs field underwent a phase transition, like water cooling and freezing into ice. It settled into a non-zero value, a specific value in the space of possible configurations. That spontaneous settling broke the electroweak symmetry. It split the once unified electroweak force into electromagnetism and the weak force. It gave mass to the W and Z bosons, but not the photon. It gave mass to quarks and electrons. It shaped the laws of physics as we experience them today. The vacuum we inhabit, the specific configuration of the Higgs field's expectation value, is the reason physics looks the way it does. A different vacuum, a different Higgs configuration, would produce a universe with different particle masses, different force ranges, different chemistry, or no chemistry at all. The laws of physics, as we experience them, are not written in stone. They are the properties of the specific vacuum state the universe settled into as it cooled after the Big Bang. And that state, with all the physics it encodes, is a property of empty space. The vacuum is not just the stage on which physics happens. The vacuum determines what physics is possible. The Higgs field is not an exotic addition to reality. It is an essential feature of the vacuum, of the nothing that isn't. Now comes the part that took physicists decades to fully confront. The zero-point energy of the vacuum is not just present, it should be enormous. When you calculate, using quantum field theory, the energy density of the vacuum, due to all those fluctuating fields and virtual particles, you get a number. And the number is disturbingly large. The most naive calculation, adding up the zero-point energies for all the quantum fields across all frequencies up to the highest energy scales where we think our physics remains valid, gives a vacuum energy density of approximately 10 to the 113 joules per cubic meter. That's a 10 with 113 zeros after it. If you're more conservative, and assume our quantum field theory only holds up to the energy scales we've actually probed in particle accelerators, you still get something on the order of 10 to the 46 joules per cubic meter or higher. Either way, the number is staggering. An energy density that would make the interior of a neutron star look empty by comparison. That is what quantum field theory predicts for the energy density of the vacuum. That is the theoretical value. And here is where the problem begins. Because when we actually measure the energy density of the vacuum, by looking at how it affects the expansion of the universe, we get a very different number. The measured vacuum energy density is approximately 6 times 10 to the negative 27 kilograms per cubic meter, which translates to an energy density of about 6 times 10 to the negative 10 joules per cubic meter. Compare that to the theoretical prediction of 10 to the 113. The discrepancy is about 123 orders of magnitude, a factor of 10, followed by 123 zeros. No other prediction in the history of science has been so spectacularly wrong in absolute terms. The theory that correctly predicts the Lamb shift to 10 decimal places cannot even get the vacuum energy within a factor of 10 to the 123 of the measured value. The ratio between the theoretical prediction and the observed value is so large it doesn't fit comfortably into any analogy. It would be like predicting that a grain of sand weighs as much as the entire observable universe, and being wrong by a similar factor again on top of that. The vacuum energy is real. We can measure it indirectly through its effect on the cosmos. But what we measure is almost nothing compared to what the theory says it should be. Something cancels most of that vacuum energy. Some mechanism, completely unknown to current physics, reduces the theoretical value by that incomprehensible factor, and then leaves a small residue. That small residue, that fraction of what should be there, is what we measure as dark energy. What that cancellation mechanism is, nobody knows. The standard model of particle physics, one of the most successful theories in science, offers no explanation. Every approach that has been tried produces either the wrong answer or no answer. String theory offers a possible framework for understanding this, involving a vast landscape of possible vacuum states, each with different energy densities. But the specific value we observe has not been derived from first principles. The cosmological constant problem, as this discrepancy is called, sits at the intersection of quantum mechanics and general relativity, two theories that both work extraordinarily well in their respective domains. And they disagree, catastrophically, about what the vacuum weighs. This is sometimes called the worst theoretical prediction in the history of physics. Not because the theory is wrong about what's there, but because the theory doesn't know why the answer isn't vastly, catastrophically more than it is. The vacuum has energy. We know that. We measure it. We just don't understand why it isn't so enormous that it would have torn the universe apart in its first fraction of a second. And that gap in understanding is one of the deepest, most humbling, open questions in all of science. There is a concept in theoretical physics that attempts to explain why our vacuum energy is what it is, rather than why it's so different from the theoretical prediction. It's called the string theory landscape. String theory, the framework that attempts to unify all forces and particles as different vibration modes of tiny strings of energy, predicts that there are an astronomically large number of possible vacuum states, different configurations of extra dimensions, different values of various fields in their ground states, different values of the cosmological constant. The number of distinct vacuum states in the string landscape is estimated to be around 10 to the 500. That number is so large, it defies any real comprehension. Each state corresponds to a different universe, a different set of physical laws, different particle masses, different forces, different values of the vacuum energy. In most of those states, the vacuum energy is large, either very positively large, producing a universe that expands so fast that matter never forms, or very negatively large, producing a universe that collapses almost immediately after the Big Bang. Only in a tiny fraction of those states is the vacuum energy small enough that a universe like ours can exist. Only in those states do galaxies form, stars burn, planets form, chemistry happen, and life become possible. The argument then goes, we should not be surprised to find ourselves in one of those rare states, because only in those states could there be anyone to be surprised. This reasoning is called the anthropic principle. The observed properties of the universe are constrained by the fact that observers are asking about them. You can only be here to observe the vacuum energy if you're in a universe where the vacuum energy permits your existence. This argument is controversial. Some physicists find it compelling. A natural explanation, given the landscape, for why we observe a small but non-zero vacuum energy. Others find it unsatisfying. It doesn't predict the specific value, only that it should be small enough to permit observers. And it requires accepting an enormous number of other universes we can never observe or test. A multiverse. Whether the landscape and the multiverse are real physics or an unfalsifiable metaphysical story is actively debated. But the question it addresses is real. Why is our vacuum energy what it is? The cosmological constant problem, the most embarrassing number in physics. The vacuum is at the center of this debate. Understanding it fully may require understanding whether our universe is one of many, each with its own vacuum, each with its own physics, or whether something else, some symmetry or mechanism we haven't found yet, explains why our vacuum is what it is. The answer, when it comes, will likely be one of the most significant discoveries in the history of science. What we can say with confidence is this: the small amount of vacuum energy that does remain after whatever cancellation mechanism operates, that residue is not zero. It exists. It has been measured. It is real. And it is causing the universe to accelerate its expansion. In 1998, two independent teams of astronomers were studying Type Ia supernovae. These are stellar explosions that result from a specific type of event. A white dwarf, the dense remnant of a dead star that has been pulling material from a companion star, accumulates mass until it exceeds a critical limit called the Chandrasekhar limit, about 1.4 times the mass of the Sun. At that point, nuclear fusion ignites catastrophically throughout the star's interior. The result is a thermonuclear explosion that briefly outshines the entire galaxy the white dwarf lived in. What makes Type Ia supernovae useful for cosmology is that the peak brightness of these explosions is related to how rapidly they fade. Brighter explosions fade more slowly. This relationship allows astronomers to work out the true brightness of a Type Ia supernova and then compare it to the observed brightness to determine the distance. The two teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory and one by Brian Schmidt at the Australian National University and Adam Rees, were making these measurements to study how the universe's expansion has changed over time. They expected to find that the expansion was slowing down. Gravity pulls matter together. The gravity of all the matter in the universe should be pulling every galaxy toward every other galaxy. That pull should be gradually decelerating the expansion left over from the Big Bang. The question was not whether the expansion was slowing, but how fast. How dense is the universe? How much matter is there? How much will gravity eventually slow things down? Instead, they found the opposite. The expansion is accelerating. Distant supernovae were fainter than they should be if the expansion were constant. They were farther away than expected. The universe's expansion had been slower in the past and is faster now. Space is expanding more rapidly today than it did several billion years ago. Something is pushing space itself outward. Something with a repulsive gravitational effect. Something that acts against the attraction of gravity on the largest scales. Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011 for this discovery. What is pushing the universe apart is called dark energy, and its properties are remarkably consistent with what you'd expect from vacuum energy. A low-level, omnipresent energy density of empty space, present everywhere equally, not thinning out as the universe expands, acting against gravity on the largest scales. The universe's expansion has been mapped by multiple independent methods since 1998. Data from the Baryon Oscillation Spectroscopic Survey, which mapped the three-dimensional positions of over 1 million galaxies, confirms it. Data from the cosmic microwave background, the afterglow radiation from the early universe, measured by the Planck satellite, confirms it. Data from weak gravitational lensing surveys, which map the distribution of dark matter by its gravitational bending of light, confirms it. Every method that can probe the large-scale structure of the universe points to the same conclusion. Dark energy makes up approximately 68% of the total energy content of the universe. All the stars, galaxies, planets, and visible matter you can see, everything built from atoms and light, makes up only about 5%. Dark matter, the invisible substance revealed by its gravitational effects on galaxies and clusters, accounts for roughly 27%. The thing that dominates the universe, the thing that controls its ultimate fate, is the energy of empty space. The vacuum is the most abundant substance in the cosmos. Not by a little, by an enormous margin. Everything we have ever seen, everything we have ever touched, every atom of every star and planet and living thing, all the photons that have ever been emitted and detected, is a tiny fraction of what exists. And the rest is the vacuum. The story of how dark energy was accepted by the scientific community is itself remarkable. In 1917, Albert Einstein added a term to his equations of general relativity. He called it the cosmological constant. He added it for a reason that turned out to be wrong. At the time, the prevailing belief was that the universe was static, not expanding, not contracting, just there, eternal and unchanging, on the largest scales. But Einstein's equations, without any additional term, predicted a universe that would either expand or contract. Gravity is attractive. Without something to counteract it, matter pulls together. The universe should collapse. Einstein added the cosmological constant as a repulsive term to balance gravity. A static universe in equilibrium. Then, in 1929, Edwin Hubble published measurements showing that distant galaxies are moving away from us. The universe is expanding, not static. Einstein called the cosmological constant his greatest blunder. He removed it from his equations. The universe didn't need a static balance between gravity and repulsion. It was expanding from the Big Bang. The cosmological constant was abandoned for decades. Most physicists assumed it was zero. No physical mechanism required it. Then, quantum field theory developed. And quantum field theory predicted that the vacuum should have an energy density. That vacuum energy acts exactly like a cosmological constant. It contributes a uniform energy density to all of space. It has a repulsive gravitational effect. Physicists recognize the connection. The cosmological constant was not zero. It was whatever the vacuum energy was. And the cosmological constant problem, the discrepancy between the theoretical and observed values, became one of the central puzzles of physics. Even before dark energy was discovered, physicists knew that whatever vacuum energy was, it was far smaller than theory predicted. That itself was a mystery. Then, in 1998, the supernova measurements showed it wasn't zero. It was small, tiny by theoretical standards, but definitively not zero. Einstein's greatest blunder turned out not to be a blunder. It turned out to be a prediction of something real. Just not for the reason he added it, and not with the value he imagined. The cosmological constant is back. and it corresponds to the energy of empty space. There is a connection between the quantum vacuum and the structure of the universe we see today that is perhaps the most profound of all. It connects the smallest scale of quantum fluctuations to the largest structures in the observable cosmos. And it runs through a period called inflation. In the first tiny fractions of a second after the Big Bang, the universe was extraordinarily hot and dense. All the energy in the universe was compressed into an unimaginably small volume, far hotter than anything we can recreate in any particle accelerator, far denser than anything that exists today. At those energies, physicists believe that a field, usually called the inflaton field, was displaced from its lowest energy configuration, not at its ground state, not at its minimum energy. It was at some higher value, a kind of plateau, rolling slowly down toward its minimum, like a ball on a very shallow, very long hill. In that state, the inflaton had a large vacuum-like energy density. And vacuum energy, as we've established, doesn't slow down expansion. It accelerates it. Specifically, it produces a form of exponential expansion. The universe, driven by the vacuum-like energy of the inflaton field, expanded at an extraordinary rate. In an interval of time, perhaps around 10 to the negative 32 seconds, the universe grew by a factor of at least 10 to the 26. It may have grown by far more. Whatever the exact details, the expansion was stupendously rapid, far faster than the speed of light. Not because anything moved through space faster than light, which would violate relativity, but because space itself was expanding. The distance between any 2 points grew at a rate that exceeded the speed of light. This period is called inflation. And while we don't yet have direct proof that it happened in exactly this way, the observational evidence is strongly consistent with it. The patterns we see in the cosmic microwave background match the predictions of inflationary models with remarkable precision. The universe's geometry is extremely close to flat. The density of the universe is almost exactly the critical density, the value at which the universe's geometry is flat rather than positively or negatively curved. The horizon problem, the fact that regions of the universe too far apart to have ever been in contact look almost identical in temperature, is naturally explained by inflation if they were once much closer together. But the most profound consequence of inflation, the one that connects it directly to what we've been exploring, is what it did with the quantum vacuum. The expansion was so rapid that tiny quantum fluctuations, the same quantum jitter that underlies the Casimir effect and the Lamb shift, were stretched from microscopic scales to cosmological ones. Vacuum fluctuations that were operating at scales far smaller than a proton were inflated outward to scales of millions or billions of light years. They became slight variations in density across the early universe. Regions where the quantum jitter happened to produce slightly more energy became slightly denser. Regions where it produced slightly less became slightly less dense. The variations were tiny, about 1 part in 100,000. But they were real, and they were permanent, imprinted on the universe as the inflaton field finished rolling to its minimum and inflation ended. Those variations were the seeds of everything. Over hundreds of millions of years, gravity amplified them. Slightly denser regions attracted more matter from their surroundings. They grew denser still. More mass means stronger gravity. Stronger gravity attracts more mass. The process compounds. Eventually, the denser regions collapsed into the first stars, the first galaxies. Those galaxies clustered, merged, formed the vast cosmic web of filaments and voids we see when we map the universe on the largest scales. The large-scale structure of the observable universe, the way galaxies are arranged in sheets and filaments and clusters separated by enormous voids, is the inflated and amplified imprint of quantum vacuum fluctuations from before any star existed, before any atom existed, before the universe was even a second old. The void is not where the universe started. The void is what the universe has been filling in ever since, sculpted by quantum noise from its earliest moments. The position of every galaxy you can see in the night sky traces back to a quantum fluctuation in the vacuum of the very early universe. Not metaphorically. Literally. The structure of the cosmos was written by the quantum vacuum, and we are reading it billions of years later through telescopes. There's one more thing the vacuum was involved in the early universe, that deserves consideration. The mystery of why there is matter at all. When the Big Bang occurred, the energy released was symmetric. For every process that produces matter, the fundamental physics we know predicts an equal process that produces antimatter. Matter and antimatter are created in pairs. An electron always comes with a positron. A proton always comes with an antiproton. This follows from the symmetries of quantum field theory. So the early universe, filled with the most intense energy ever in the cosmos, should have created equal amounts of matter and antimatter. And when matter and antimatter meet, they annihilate, convert entirely to radiation. A universe with equal amounts of matter and antimatter would have annihilated itself entirely as it cooled. Proton meets antiproton. Electron meets positron. All gone. Just radiation remaining. A universe of photons and nothing else. No atoms. No stars. No galaxies. No you. Yet, here we are. The universe contains matter. Not equal amounts of matter and antimatter. Vastly more matter than antimatter. For every billion antiparticles produced after the Big Bang, there were 1,000,000,001 particles. One extra. When the annihilation was finished, one particle in 1,000,000,000 remained. Those survivors are everything. Every atom in every galaxy. Every star and planet. Every living thing. The asymmetry between matter and antimatter, one of the deepest unsolved problems in physics, is called baryogenesis. We know the asymmetry exists. We know the general requirements for generating it, formulated by the physicist Andrei Sakharov in 1967. But the standard model of particle physics doesn't contain enough asymmetry to explain what we observe. There must be physics beyond the standard model that produced the matter-antimatter asymmetry. The quantum vacuum is suspected to be involved. Transitions in the vacuum state in the early universe, changes in the Higgs field configuration, could in principle generate net matter. The electroweak phase transition, the moment when the Higgs field settled into its non-zero vacuum expectation value, may have been the moment when the asymmetry was generated. Whether this happened, and in enough quantity to explain the observed asymmetry, is an open research question. But the vacuum, once again, is at the center of the story. The reason there is matter in the universe, the reason you exist, may ultimately be a consequence of how the vacuum transitioned from one phase to another in the first fractions of a second after the Big Bang. Now, there is one more thing happening in the vacuum that deserves attention, because it shows just how active empty space really is when you put it near something extreme. In quantum electrodynamics, virtual particles come in pairs. An electron and its antiparticle, a positron, a quark and an antiquark, a photon and another photon. They appear together from a vacuum fluctuation, connected to each other, bound to recombine. They exist for a moment, borrowing energy from the uncertainty principle. Then they find each other again and annihilate, releasing the energy back into the vacuum. This happens constantly, everywhere, at every point in space. In ordinary empty space, far from any mass or energy concentration, these pairs appear and annihilate so quickly and symmetrically that nothing net happens. The vacuum looks stable. The borrowed energy is returned before anything outside can notice. No net energy is created. No net particles produced. But in 1974, the physicist Stephen Hawking applied quantum field theory to the region near the event horizon of a black hole. An event horizon is the surface beyond which, once crossed, nothing can return. Not light. Not information. Not particles. It's not a physical surface. There's nothing there you could touch. It's a geometric boundary in space-time, the point of no return. Inside the horizon, all possible paths in space-time lead toward the singularity. There is no direction in space you can point that leads outward. Even light, heading in any direction, ends up falling further in. When Hawking analyzed what the quantum vacuum does near this kind of boundary, he found something nobody expected. Near the horizon, the gravitational field of the black hole is intense enough to separate a virtual pair before the two particles can annihilate. One particle falls inward, crossing the horizon, entering the black hole. The other particle escapes outward, away from the black hole. The escaping particle has nowhere left to annihilate with its partner. Its partner is behind the horizon, gone, in the only meaningful sense that matters. So the escaping particle becomes real, a genuine particle with real energy, departing the region near the black hole and traveling outward. From outside the black hole, this looks exactly like the black hole is radiating, emitting particles, losing mass, losing energy. This is called Hawking radiation. The energy for these escaping particles comes ultimately from the mass of the black hole. The infalling partner carries negative energy relative to a distant observer, which is consistent with the curved geometry near the horizon. The net effect is that the black hole slowly loses mass. A stellar mass black hole, one formed by the collapse of a massive star, would take an incomprehensibly long time to evaporate in this way. Far, far longer than the current age of the universe. For a black hole of 10 solar masses, the evaporation time would be about 2 times 10 to the 70 years. We have never detected Hawking radiation directly. For any black hole we could currently observe, the temperature of the radiation would be so low it would be swamped by the cosmic microwave background. A stellar mass black hole emits Hawking radiation at a temperature of about 6 billionths of a Kelvin. Unmeasurable with any current or foreseeable instrument. But the mechanism itself is physically compelling. And Hawking radiation is taken seriously as a real phenomenon by essentially all physicists who have studied it, because the mechanism is rooted entirely in vacuum physics. The black hole doesn't emit anything from inside it. Nothing crosses the event horizon outward. The energy comes from the vacuum near the horizon, from virtual pairs that get separated by the geometry of curved spacetime. The vacuum, again, is not passive. It interacts with mass, with gravity, with the geometry of space itself. It responds to what surrounds it. And in the most extreme case, it slowly erases even the most powerful objects the universe produces. Black holes are not permanent. They are subject to the quantum vacuum. Everything is. There's an environment in the universe where the quantum vacuum is being stressed in a way almost nothing else can match. Magnetars. A magnetar is a type of neutron star with an extraordinarily powerful magnetic field. Neutron stars themselves are already extreme objects. The collapsed remnants of massive stars. Objects about 20 to 25 kilometers across, containing more mass than the Sun, compressed to such density that the matter inside is mostly neutrons packed together. But magnetars go further. Their magnetic fields reach strengths of 10 to the 14 to 10 to the 15 Tesla. For comparison, a strong hospital MRI machine produces fields of about 1 to 3 Tesla. The magnetic fields on magnetars are roughly 100 trillion times stronger. At those field strengths, quantum electrodynamics predicts something strange happens to the vacuum. In ordinary conditions, the vacuum is optically isotropic. Light, polarized in any direction, travels at the same speed. The vacuum looks the same from every polarization angle. But, in a sufficiently strong magnetic field, virtual electron-positron pairs in the vacuum become polarized. They align with the field, like tiny antennas. And their alignment makes the vacuum birefringent. Light polarized parallel to the magnetic field travels at a slightly different speed than light polarized perpendicular to it. The vacuum, in the presence of an extreme magnetic field, acts like a crystal, rotating the polarization of light passing through it. This effect was predicted by quantum electrodynamics decades before it was confirmed. It was observed for the first time in 2017 using observations of X-ray light from the neutron star RxJ 1856.5-3754 with the Very Large Telescope in Chile. The light showed a degree of linear polarization consistent with vacuum birefringence. The vacuum of space, in the presence of a powerful enough magnetic field, rotates the polarization of light. The nothing between us and the neutron star is not optically neutral. It responds. It has properties. It leaves a measurable imprint on the light passing through it. The vacuum is not empty. Understanding what fills the vacuum also forces a rethinking of what matter really is. Because if you go small enough into matter itself, you find that the distinction between matter and vacuum starts to blur. You were probably taught at some point that atoms are mostly empty space. A tiny nucleus in the center, electrons somewhere outside. The nucleus takes up a tiny fraction of the atom's volume. This description is geometrically accurate. The nucleus of an atom is roughly 10 to the negative 15 meters across. The electron cloud extends to about 10 to the negative 10 meters. The nucleus occupies a volume about 10 to the 15th times smaller than the atom. If you scaled the hydrogen atom up to the size of a large sports stadium, the nucleus would be a marble sitting in the center, and the electron would be a speck somewhere in the bleachers. Most of the atom is, in the geometric sense, empty. That description is technically accurate. But it misses something important. The interior of an atom is not empty in any meaningful physical sense. It is filled with quantum fields. The electron doesn't orbit the nucleus in a fixed path the way a planet orbits a star. The electron is described by a quantum wave function, a probability amplitude that fills the entire region around the nucleus simultaneously. The electron field is present throughout the atom. The electromagnetic field fills it. Virtual photons are constantly being exchanged between the nucleus and the electrons. The force holding the electron in orbit around the nucleus is mediated by those virtual photons. Without the virtual photon exchange, without that constant activity in the supposedly empty space inside the atom, the electron would not be bound. The atom would not exist. The nuclei of atoms, which make up the hard, dense core of matter, are themselves not empty either. A proton is not a solid ball of stuff. It is made of quarks, 3 of them, and those quarks are held together by the strong nuclear force mediated by gluons. But the quarks account for only a small fraction of the proton's mass. The masses of the 3 quarks inside a proton add up to about 9 to 14 mega-electron-volt, depending on exactly which values you use for the quark masses. But a proton actually weighs about 938 mega-electron-volt. The rest, more than 90% of the proton's mass, comes from the energy of the gluon field that holds the quarks together. The gluon field is a quantum field. It fills the interior of the proton with constant activity. Virtual gluons being exchanged. Virtual quark-antiquark pairs appearing and vanishing. Energy stored in the curvature and tension of the color field. The proton is not mostly matter. It is mostly field. It is mostly what fills the space between the quarks. The atom is not mostly nothing. It is mostly field. Your mass does not come from solid stuff sitting in otherwise empty space. Your mass comes primarily from the energy of quantum fields distributed through what we used to call emptiness. The thing you call matter is mostly quantum vacuum activity. The distinction between matter and the void is far less sharp than it appears from the outside. You are, in the most literal physical sense, mostly made of what we thought was nothing. There's a direct line from the quantum vacuum to technology you use every day. Consider why atoms emit light. An atom in an excited state will, after some time, spontaneously emit a photon and fall to a lower energy state. This is called spontaneous emission. It's why excited atoms glow. It's why heated objects emit thermal radiation. It's why neon signs glow when a current passes through them. For a long time, this spontaneous emission was hard to explain. An excited atom sits in empty space. Why would it spontaneously emit a photon if nothing is perturbing it? There's no obvious external trigger. The answer came from quantum electrodynamics. The vacuum is not truly empty around the atom. Virtual photons are constantly flickering in and out of existence in the vacuum. These vacuum fluctuations interact with the excited atom, stimulating it to emit. Spontaneous emission is not truly spontaneous. It is stimulated emission, triggered by the quantum vacuum. The vacuum is the trigger. Every photon emitted spontaneously from every atom in the universe is a consequence of the quantum vacuum doing what it always does. The light from every star. The heat radiation from every warm object. The glow of every flame. All of it traces back to the vacuum, stimulating atomic emissions. LED lights. The light sources in almost every screen and illumination device in the modern world emit light through this process. Electrons in semiconductors fall from higher energy states to lower ones, emitting photons as they fall. The quantum vacuum is what triggers those emissions. It's why the screen you might be watching this on glows. Not directly, not in a way the engineers need to calculate explicitly. But the physics underlying the device depends on the vacuum. Lasers operate on stimulated emission, photons triggering other photons. But they start from spontaneous emission triggered by the vacuum. The first photon in any laser, the seed photon, is a vacuum-triggered event. The quantum vacuum is the hidden hand behind the technologies we build from light. There's a field of technology being built right now that depends critically on the quantum vacuum in a way most of its practitioners think about every day. Quantum computing. Classical computers process information using bits. Each bit is either 0 or 1. A voltage is either high or low. A magnetic domain points either up or down. Quantum computers process information using quantum bits, called qubits. A qubit can be in a superposition of 0 and 1 simultaneously. It can be in a complex combination of both states at once, until it's measured. This quantum superposition is what gives quantum computers their potential power. But there's a fundamental challenge. Superpositions are fragile. Any interaction with the environment, any disturbance from the outside world, collapses the superposition, destroys the quantum state, makes the qubit behave like a classical bit. This is called decoherence. And one of the main sources of decoherence is the quantum vacuum itself. The vacuum fluctuations that cause spontaneous emission, the same vacuum fluctuations responsible for the Lamb shift and the Casimir effect, interact with the qubits. They perturb the quantum states. They introduce noise. They cause errors. Quantum computers need to be isolated from the quantum vacuum's fluctuations as much as possible. This is one reason quantum computers are operated at extraordinarily low temperatures. Dilution. Refrigerators cool the chips to about 10 to 15 millikelvin, which is about 100 times colder than outer space. At those temperatures, the thermal fluctuations from the environment are suppressed. But the quantum vacuum fluctuations are always present. They can't be suppressed. They are irreducible. Engineers designing quantum computers have to account for them. Error correction codes in quantum computing are partly designed to deal with the decoherence introduced by vacuum fluctuations. The quantum vacuum is an active engineering challenge in one of the most advanced technologies humans are currently trying to build. The nothing that isn't nothing is preventing the computers of the future from working as well as they could. There's a practical question that comes from all of this, and it's one people ask regularly. If the vacuum has energy, can we extract it? Can we tap into zero-point energy? This idea circulates regularly in popular science, sometimes in connection with ideas about free energy devices. The honest answer is almost certainly not, for reasons rooted in the very physics we've been exploring. The zero-point energy of the vacuum is the minimum possible energy, the floor. You can't extract energy from something by putting it into a lower energy state if it's already at the lowest state it can be. A ball sitting at the bottom of a valley has no energy to give up relative to the floor of that valley. You could extract energy by lowering the floor, But the vacuum energy is defined relative to the lowest accessible state of all the fields. There's nothing below it to lower it to. You can manipulate the vacuum energy locally, as the Casimir effect demonstrates. By imposing boundary conditions, you change the balance of vacuum modes and create forces. But those forces are conservative. They can do work when plates move together. But they don't let you extract net energy from a closed system. If you let the plates come together under the Casimir force, you gain a tiny amount of kinetic energy. But then, you have to put energy in to pull them apart again. The system is conservative, just like any other potential energy. You don't get something for nothing. And any manipulation you do to reduce vacuum energy in one region increases it elsewhere to compensate. Energy is conserved. Even vacuum energy obeys that. The quantum vacuum is not a free lunch. It is an irreducible minimum. It does things. It affects the world. It mediates forces. It shifts energy levels. It exerts pressures, but it doesn't hand over its energy on request. The physicist Richard Feynman, who was more quotable than most, once described the vacuum as containing an enormous amount of energy in every cubic centimeter, more than enough to boil all the world's oceans. But it's the basement. You can't get below the basement. This brings us to something that sits at the edge of what physics currently understands: the nature of space itself. When we talk about the vacuum fluctuating, about virtual particles appearing and disappearing, about fields filling all of space, we're implicitly assuming that space is a fixed, continuous background, a smooth stage on which all of this happens. But quantum mechanics and general relativity, when you try to combine them at the smallest possible scales, suggest that space-time itself may not be smooth. At the Planck length, roughly 1.6 times 10 to the negative 35 meters, scales far smaller than any particle we've ever probed, the assumptions of continuous smooth space may break down completely. The Planck length is obtained by combining the three fundamental constants of nature: the speed of light, Planck's constant, and Newton's gravitational constant. It's the scale at which quantum effects and gravitational effects become equally important. It's the scale below which our current theories stop working. We don't know what's below it, but the arguments from quantum mechanics and gravity suggest something unsettling. At the Planck scale, space-time itself might be granular, foamy, constantly fluctuating in its very geometry, not just in the fields that live within it. This is sometimes called quantum foam, a term coined by physicist John Wheeler in the 1950s. Wheeler imagined that at the Planck scale, the smooth space we experience is actually built from something that at the smallest scales looks like a chaotic, bubbling foam, tiny curvatures appearing and vanishing. The topology of space changing from moment to moment. Wormhole-like structures forming and collapsing on timescales of about 5 times 10 to the negative 44 seconds, the Planck time. The smooth space we experience on human scales, and even at the scale of atoms and nuclei, would then be a kind of emergent smoothness, an average over the turbulent microscopic structure. The way the surface of water looks smooth from a distance, even though it's made of jostling molecules. We don't have experimental access to the Planck scale. No particle accelerator we could build would probe energies that high. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 14 tera-electron volt. The Planck energy is about 1.2 times 10 to the 19th giga-electronvolt. That's about 10 to the 15 times the Large Hadron Collider's energy. We cannot directly confirm whether space-time is foamy in this way. It may never be directly testable. But several approaches to quantum gravity, the still elusive theory that would unify general relativity and quantum mechanics, suggests that space-time at the Planck scale is indeed not smooth. Loop, quantum gravity. One of the serious attempts to quantize space-time predicts a discrete structure, a minimum area, a minimum volume, not a continuous manifold, but a network of discrete quantum states. String theory predicts that below the string scale, which may be near the Planck scale, the concept of space-time as a smooth background ceases to be well defined. The vacuum, in this picture, is not just filled with quantum fields. It is itself a quantum object. Space and time are not a fixed background. They are dynamic, fluctuating, quantum mechanical entities whose smoothness at everyday scales conceals a turbulent quantum foundation. The stage is part of the play, and we don't yet know what the stage is made of. Here is what makes all of this strange, in a way that goes beyond the technical details. We built our entire intuition about the world on the idea of substance. There is stuff, and there is the space between the stuff. The stuff is real. The space is where the stuff isn't. Simple, clean. That intuition worked for all of human history until the 20th century. It made sense because on human scales it works. The table is real. The air around it is nearly nothing. The gap between atoms is, for practical purposes, empty. Nothing in everyday human experience contradicts this picture. But go smaller, go deeper, go more carefully. And what you find is that the thing you called the space between the stuff is the most fundamental thing of all. The fields exist everywhere. The matter, the particles, the atoms and molecules, those are the local disturbances, the excitations. The stuff you can see and touch is the exception. The background field, the quantum vacuum, is the rule. It's everywhere. It's always doing something. It cannot be turned off. It cannot be reduced to zero. It cannot be removed. It is more fundamental than the particles that live in it. In a sense, the particles are made of it. They are excitations of the fields that fill the vacuum, temporary patterns in the quantum substrate. Matter as a disturbance in what we used to call nothing. The empty space was never the background. It was always the substance. Now the vacuum also connects, in a way most people haven't considered, to a very old question. Why is there something rather than nothing? This is one of the oldest questions in philosophy. Leibniz asked it in the 17th century. Probably humans asked it long before that. It seems like a genuinely profound puzzle. Given a universe that contains things, one might imagine the alternative, where it contains nothing. And the question is, why the one rather than the other? Modern physics has something new to say about this, though it doesn't fully resolve the question. If the vacuum can spontaneously produce particle pairs, if it seethes with activity and energy even in the absence of anything else, then the notion of a true nothing, a state with no fields, no energy, no fluctuations, becomes scientifically problematic. The physicist Lawrence Krauss made this argument prominent in the early 2010s. And while some philosophers found the argument incomplete, it points to something real. The quantum vacuum is the closest thing to nothing that nature seems to permit. And even it is not nothing. It has energy. It fluctuates. It can produce particles. It has a structure. It responds to geometry. A true nothing, a state with no quantum fields, no geometry, no possibility of fluctuations, may not be something that can exist even in principle. Not because something prevents it from existing, but because the laws of quantum mechanics don't allow for a state that is genuinely zero in every meaningful sense. The uncertainty principle won't allow it. The fields can't be completely suppressed. Energy can't be zero everywhere at once. In this view, the existence of something is not a surprise, requiring explanation. It might be the only possibility. Nothingness might simply be forbidden. That is a remarkable thing to contemplate. Not that something was created from nothing, but that nothing was never available as an alternative. The universe exists not because something caused it to exist, but because the alternative, a genuine absence, is not physically possible. Even the question of why there is something rather than nothing may be the wrong question. Not because it's unanswerable, but because the premise that nothingness is available may not be true. This is not a settled conclusion. It is an active area of philosophical and physical debate. But it is a different conversation than the one you'd have had 2 centuries ago. And it begins with the vacuum, with what fills empty space, with what the vacuum is. The implications for the future of the universe are also strange and long. The universe is expanding. That much is certain. But how it expands over cosmic time depends critically on what the vacuum energy is and whether it changes. The simplest assumption, and the one consistent with current observations, is that the vacuum energy is a cosmological constant, a fixed property of space, the same at all times and in all places. In that case, as the universe expands, matter and radiation thin out, but vacuum energy doesn't. It is a property of space, and as more space comes into existence through expansion, the total amount of vacuum energy increases proportionally, keeping its density constant. The ratio of vacuum energy to everything else keeps increasing. Dark energy becomes more and more dominant. The universe expands faster and faster. Distant galaxies recede beyond the cosmic horizon, the distance beyond which nothing can ever reach us, because the space between us is expanding faster than light can cross it. One by one, galaxy cluster by galaxy cluster. The observable universe shrinks as things fall beyond that horizon forever. In this scenario, sometimes called the Big Freeze, the universe eventually reaches a state where all usable energy has been dissipated. Stars have burned out. Protons, if they are unstable as some theories predict, have decayed into lighter particles. All the black holes that remain have eventually evaporated via Hawking radiation, releasing their mass as thermal radiation. All that remains is an expanding vacuum, cooling toward, but never quite reaching absolute zero, with nothing left to form structure or complexity. The quantum fluctuations continue. Virtual particles appear and vanish. But there's nothing for them to interact with. The universe is still active at the deepest level, still fluctuating, but empty of everything we'd recognize as structure or complexity or life. An eternal quantum murmur in an ever-expanding void. That is one possible future. There are others, more dramatic and more immediate. Some physicists have speculated that the vacuum we exist in is not the true lowest energy state. That there is a lower energy vacuum available, a state of the Higgs field, different from the one we inhabit, that corresponds to a different set of physical laws. And that our vacuum could, through quantum tunneling, suddenly, and without warning, transition to that lower state. This is called vacuum decay, or false vacuum decay. The idea is that our universe sits in a metastable vacuum, a local energy minimum, but not the global minimum. Quantum mechanics allows systems to tunnel through energy barriers to lower states. If our vacuum is metastable, then somewhere in the universe, at some unpredictable moment, a quantum fluctuation could seed a bubble of the true vacuum. A small region of space where the Higgs field has tunneled to its true ground state. Inside that bubble, all the constants of physics would be different, almost certainly incompatible with the existence of atoms, chemistry, or anything else we know. The bubble would expand outward at the speed of light. The boundary between our vacuum and the true vacuum would be a thin shell, propagating at light speed in all directions. Inside the bubble, the known universe would be replaced by something unrecognizable. The transition itself would not be experienced. Nothing inside the bubble can signal anything about its arrival. Light, traveling at the same speed as the expanding bubble, cannot outrun it. If vacuum decay is happening somewhere in the universe right now, we would not know until the moment it arrived here. There would be no warning. We don't know whether our vacuum is stable or metastable. Measurements of the Higgs boson mass and the top quark mass, the two quantities that most directly determine the stability of the Higgs field's vacuum, feed into calculations of the vacuum's stability. Current best estimates put our vacuum in an intriguing position. The values of the Higgs mass and top quark mass measured at the Large Hadron Collider put the universe in or very near the boundary between a stable and a metastable vacuum. The uncertainties in the measurements don't allow a definitive conclusion. The vacuum might be stable forever, or it might be sitting in a metastable state, waiting for a quantum fluctuation that hasn't happened yet. If it is metastable, the transition could happen anywhere in the universe at any time. But the timescale, if our estimates of the potential are correct, is likely much longer than the current age of the universe. So the concern, while scientifically real, is not an immediate practical one. But the possibility itself is a consequence of taking vacuum physics seriously, of understanding that the vacuum is not nothing, that it has a structure, a potential energy landscape, and that structures can change. The quantum vacuum is the most studied nothing in history. It has produced more experimental results, more theoretical machinery, more Nobel Prizes than almost any other topic in physics. The Lamb shift led to the precision development of quantum electrodynamics, which produces predictions matching experiment to more than 10 significant figures. The Casimir effect is now relevant to engineering at the nanoscale. The Higgs mechanism, which explains mass as arising from the interaction with the vacuum's non-zero Higgs field, was proposed in the early 1960s and experimentally confirmed 50 years later in one of the most expensive and technically ambitious experiments in history, the search for the Higgs boson at the Large Hadron Collider. Dark energy, the vacuum energy, driving cosmic acceleration, was discovered in 1998 and has remained the central mystery of cosmology ever since. Hawking radiation, while undetected directly, has shaped decades of theoretical work on the relationship between quantum mechanics, gravity, and the nature of information inside black holes. And inflation, which uses vacuum-like energy to explain the large-scale structure of the universe, is the leading framework for understanding the universe's origins. Tested against the most detailed observations of the cosmic microwave background. All of this from asking, what fills empty space? All of this from noticing that the vacuum does things it shouldn't do if it were truly nothing. All of this from following the implications of quantum mechanics into territory where common sense fails and the universe turns out to be stranger and more interesting than it appeared. The pattern here is not subtle. Every time physics has looked more carefully at nothingness, it has found something. Every time an experimentalist has tried to measure what the vacuum does, they have found that it does something. Step back and take honest stock of what we know and what we don't. Because the story of the quantum vacuum is partly one of the greatest triumphs in the history of science, and partly one of the deepest failures. Both things are true simultaneously. What we know is extraordinary in its precision. Virtual photons shift the energy levels of hydrogen atoms, the Lamb shift, measured to more than 10 significant figures, matched by quantum electrodynamics to the same precision, confirmed across many atoms and ion species. The quantum vacuum exerts forces on nearby conductors. The Casimir effect, measured in many independent laboratories, reproduced across a range of materials and geometries. The vacuum has a non-zero Higgs field permeating it. Confirmed by the discovery of the Higgs boson in 2012, confirmed by the measured masses of particles throughout decades of experiments. The vacuum has a non-zero energy density, confirmed by the observed acceleration of the universe's expansion, confirmed by multiple independent observation techniques. Virtual particle exchange mediates all known forces, confirmed by the extraordinary predictive success of the Standard Model, confirmed in billions of particle collisions in accelerators around the world. Inflation, driven by vacuum-like energy in the early universe, seeded the structure of the cosmos. Supported by the pattern of fluctuations in the cosmic microwave background. Supported by the large-scale structure of galaxy distributions. What we don't know is at least as striking. We don't know why the vacuum energy is as small as it is. The cosmological constant problem, the most dramatic numerical disagreement between theory and observation in all of science. We don't know whether the vacuum is stable or metastable, whether the Higgs field's current configuration is the true minimum, whether vacuum decay is possible, and if so, on what timescale. We don't know what dark energy truly is, whether it's a cosmological constant truly fixed for all time, or a dynamical field called quintessence by some theorists that changes as the universe evolves. Current measurements are consistent with a constant, but the precision is not yet enough to rule out slow variation. If dark energy varies, it would transform our understanding of the vacuum. We don't know how to describe the vacuum at the Planck scale. We don't have a quantum theory of gravity. Without it, we can't describe the vacuum at the smallest possible scales. We don't know whether space-time is smooth or discrete at the Planck scale. We don't know whether the Planck scale is even the fundamental scale, or whether there's something deeper still. These are not small questions at the margins of physics. They are central. They are what the field is actively working on, and they all concern, in one way or another, the nature of the vacuum. Empty space is not a solved problem. It is the problem. The frontier, where our understanding runs out, is precisely the question of what the vacuum is and why it is what it is. The progression has been consistent for nearly a century. In 1947, the Lamb shift showed that vacuum fluctuations shift atomic energy levels. In 1948, the Casimir effect was predicted, showing that vacuum fluctuations exert measurable forces. In the 1960s, the Higgs mechanism proposed that the vacuum's non-zero Higgs field gives mass to particles. In 1974, Hawking showed that vacuum fluctuations near black holes produce real radiation. In the 1980s and 90s, the theory of inflation was developed and confirmed, showing that vacuum fluctuations in the early universe seeded the structure of the entire cosmos. In 1997, the Casimir force was experimentally confirmed. In 1998, dark energy was discovered, confirming that the vacuum has an energy density that controls the universe's expansion. In 2012, the Higgs boson was discovered, confirming that the Higgs field has its predicted non-zero vacuum expectation value. Empty space was always a story we told ourselves because we didn't have the instruments to see what was really there. We have those instruments now. And what they show is that the most common substance in the universe, the thing that fills more of existence than anything else, the thing that everything else is embedded in, is what we used to call nothing. Nothingness that gives particles their mass. Nothingness that exerts forces. Nothingness that seeds galaxies. Nothingness that slowly erases black holes. Nothingness that may be the only state the universe is capable of occupying. Wherever you look, in whatever direction, at whatever scale, the universe is full. Here's something strange to sit with. You have never, in your entire life, directly perceived the quantum vacuum. You've never seen a virtual particle, never felt a Casimir force, never noticed the zero-point energy fluctuations beneath everything. Your senses are tuned to a world several orders of magnitude above the quantum scale. You see things because photons hit your retinas. You feel things because atoms in surfaces press against atoms in your skin. You hear things because pressure waves in air move your eardrums. All of this is happening at the scale of atoms and molecules and above. Far above the quantum vacuum scale. And yet, the quantum vacuum is why everything you perceive exists. The atoms whose surfaces you touch exist because quantum field theory, including the vacuum structure, governs how electrons bind to nuclei. Without the quantum vacuum mediating the electromagnetic force, those atoms wouldn't be bound. The photons hitting your retinas were emitted by atoms whose transitions were triggered by vacuum fluctuations. The air conducting sound to your ears is made of molecules held together by quantum fields pervading the vacuum. Every sense you have, every perception you've ever had, every experience of the physical world is downstream from the quantum vacuum. The vacuum is not somewhere else. It's not in a laboratory. It's not in deep space between galaxies. It's here, right here. The same quantum fields, the same fluctuations, the same Higgs field background, the same zero-point energy are present in this room as they are in the void between galaxy clusters. The vacuum is the most local thing about the universe. It's where you are, in it, of it, built from it. The universe doesn't have empty space with things in it. It has quantum fields everywhere, And some of those fields happen to be arranged, in a few places, into the temporary patterns we call matter, which is what you are. A temporary arrangement of quantum field excitations. A disturbance in the vacuum. Alive and aware, and wondering what the vacuum is. The progression from the Lamb shift in 1947 to the anomalous magnetic moment measured to a part in a trillion in 2023 is one of the great arcs in the history of lies. Science. Each step confirmed, with greater precision, that the vacuum is not passive, that the nothing is something, that the absence of matter is not the absence of physics. The something that fills the nothing turns out to be one of the most consequential things in the universe. It gave you your mass. It keeps your atoms together. It lit the stars. It shaped every galaxy you can see. It is driving the universe toward its ultimate fate. And it may be the reason there is a universe at all. The next time you're somewhere quiet and you imagine the space around you as still, as empty, as nothing at all, remember what's actually there. Fields threading through every point in the room. The Higgs field, present everywhere at its non-zero background value, giving mass to every particle in the walls, the floor, your body, the air. Virtual particles appearing and vanishing at a rate beyond human intuition, mediating the forces that hold every atom together. Quantum fluctuations in the electromagnetic field, pressing on every surface. Cosmic microwave background photons, from the edge of the observable universe, passing through this room right now. Neutrinos from the sun, billions of them per second, through every square centimeter of matter, passing through you as if you were transparent. And the vacuum energy itself, the cosmological constant, present here at the same density as everywhere else in the cosmos, slowly driving the universe apart. A force so weak at local scales you can't feel it, but so vast and pervasive that it dominates the energy budget of everything that exists. Empty space is not the absence of things. It is a quantum medium, filled with fields and fluctuations and energy, pervaded by forces and particles and the non-zero background that makes chemistry and life and the universe itself possible. The void is an illusion. The vacuum is the truth. And the truth is far more interesting than nothing. Good night.